Okay, so let's close the first part on cavity QED or SQUID today. We finished the things on measurements. Just to recall what we were doing the other day, we had this idea of having some cavity resonance around here, and the qubit sitting somewhere not too close, so it would be somewhere here. So there is a tuning between the cavity and the qubit. And we saw that the resonance of the cavity was shifted by an amount that depended on the state of the qubit. And there were also shifts on the resonance of the qubit itself. The idea was then that we can use this to measure the state of the qubit by sending radiation exactly at this frequency, because if the qubit is in the up state or +1, the resonance will be shifted in one direction, and if not, it will be shifted in the other direction. If the resonance is here, we will get one phase shift, and if the resonance is here, we will get another phase shift. And by monitoring the phase of the field that comes out, we could guess the state of the qubit. No? That was the idea. This can be extended to consider not just instantaneous measurement of sigma set, but to study the resonances of the qubit itself. We saw that spectroscopically we could resolve more or less the double peak structure when the qubit approaches the cavity resonance. As we saw the vacuum rapid splitting, it could be measured experimentally. But the problem is that when the qubit is far away from resonance, apart from being able to measure its state, we don't see any resonance here, because our injection of signal basically is an operator that describes the coupling between our input ports and the cavity, A and A dagger. So basically we have omega A plus A dagger. And when the qubit is far away from the cavity, these operators do not contain any admixture of qubit operator. When the qubit is close to the cavity, when we expand A and A dagger in the basis of eigenstates of our Hamiltonian, these operators, they contain matrix elements between different eigenstates that involve transitions for both the cavity and the qubit. But if the qubit is far away, then this is not true. So when we drive the cavity, we are driving the cavity, but we don't see much of an effect on the qubit itself, or at least this is not evident from the radiation that comes out, apart from the fact that we could see some changes in sigma set. So the idea is that we could, so you follow more or less this explanation. So when the qubit is far away, so this resonance is not obvious. So simply the only effect that we have is a shift of the cavity. But we would like to see what happens to the qubit itself, which has some structure, sigma set, and we could have some external field also acting on it via some antennas, and we could probe the dynamics of this qubit. We would like to probe the dynamic of this qubit even when it's not close to the cavity, to see that the qubit is there, and to see, well, what is the actual level structure of the qubit. One of the reasons why we want to do that is that if you want to do an experiment where you want to study the interaction between the qubit and the cavity, and you just have measurements around here, you don't have enough information to fit the whole hyperbola of the qubit. So you have very limited fitting parameters. So you would like to have information about the resonance of the cavity, which you already have. You would like to have information about the coupling, G, which you also have from that resonance, but you would also like to have information about the minimum gap of the qubit to really fit this model and write the full Hamiltonian describing your experiment. And well, the people in Yale that developed all these ideas of SQUID also had the idea that you could probe the dynamics of the qubit by looking at what happens to the cavity. So the idea is that you don't send just one frequency here, which would be resonant with the cavity, would be this. But you also send another driving frequency, which it's meant to excite the qubit. Okay? We saw already that when you drive with some external force a resonator, the resonator has its own dynamics and it accommodates this external force. So basically A and A dagger are going to oscillate with a linear combination of these two drivings. The closer the driving is to the resonance, the stronger the amplitude of that component. But we can compensate by increasing a little bit the power of this. Or alternatively, you could have a qubit here and have some antenna that drives it with a different mechanism. But the idea is that we are going to drive the qubit and we are going to drive the cavity. And we monitor from this first, this probe field, we monitor the phase that the qubit experiences. I'm going to show you in transparency because my drawing skills are not fantastic. Monitor the phase that the field experiences. And if we didn't have any dynamics, well, the phase would depend on the state of the qubit, right? If it's in the ground state, you get one phase shift. That's what more or less is the picture there. So for most of our qubit conditions, where we are driving with different bias fields, the output field experiences a phase shift due to the qubit being in the ground state. But when we drive with a frequency here or here that is resonant with the qubit, we can excite the qubit. And the qubit stops being in the ground state, and actually it oscillates, and this value of sigma z averages to 0. So it's the phase shift that the field is experiencing is oscillating between two positive and negative values, and that's where you see that in those peaks, there are the dips in the phase experienced by the probe field. Do you follow more or less? Okay. So if nothing happens, the qubit will simply stay in the ground state. It's away from the cavity. There is nothing that bothers it, and you get one phase shift. Would be this one. But if you now start to drive the cavity, the qubit with a given frequency, if you excite the qubit with the appropriate resonance, then it will excite, and this average of sigma z will mean that there is no significant phase shift in the output field of the cavity. And that's a way that you can really make images that complete this picture down here. So you would have where the qubit is independent of the cavity, you can have this two-tone spectroscopy to have pictures of the bottom of the hyperbola of the qubit. And together with this and this part of the spectra, you can really fit the whole J-Cummings Hamiltonian and know all the parameters from your problem. Okay, so that was just to complete a little bit the picture of that. You can really get a lot of information from these cavity experiments. We still haven't studied anything other than spectroscopy. The next type of experiment would be really time domain experiments where you monitor in a time-dependent fashion the oscillations of the cavity and the qubit. But before that, I wanted to introduce today a kind of zoology of qubits that are out there, just to discuss the ones that are being used in different experiments, and also to move away from the charged qubit that is by today's standards obsolete. Before doing that, I have to introduce also one element that I simply took for granted, which is the SQUID. This is SQUID, which is this device where you have a loop, superconducting loop with two junctions. and which is threaded by some external flux in the middle. You have seen this design, for instance, in the charged qubit experiments from Yale, where you have your superconducting island. There are two legs that connect it to a ground plane, and there is a hole through which you can inject some flux. Okay? These two junctions will be the equivalent that you have there. And what I told you is that these two junctions, together with this external flux, would be like a flux-dependent Josephson tunneling amplitude. So the combination of the two junctions with this external flux will give you a tunneling amplitude that can be modulated by this guy. I'm just going to explain it a little bit because we are going to use it later on. The idea is very simple. You have this circuit which consists of two parallel junctions with its own capacitance and nonlinear inductance. And then you have some external flux. Let's take some direction, like this could be 1. Delta phi, this is A and B. And this would be delta phi AB. And because there is a flux inside the loop, we know already that they don't have to add up to 0. Okay? Plus some possible multiples of phi 0, which we neglect right now. So this means that in reality, this doesn't have more degrees of freedom than if I had just a single junction. Because there are two flux differences, but one can be extracted from the other one. So I can write a Hamiltonian just like the other way, computing the capacitive and inductive energy, which would be just 1. Well, let's do first the Lagrangian. 2. This will be one junction. I'm using AB dot. And if this is constant, well, this is just the same term. So because BA is phi x minus delta phi AB, and really the sign goes away. So basically you are adding the two capacitive terms from the two junctions. And the trick comes when you consider the when you consider the inductive part, which contains the energy of the Josephson junctions. And this is a cosine, and this is a cosine. And you see that you have two cosines, and actually you can basically, they are displaced from each other. Okay? So you can write this, that's better here, as 2 EJ cosine phi x phi 0 cosine, just a change of variables like this, and then 2 times the capacitance just because when you add the cosines, then you get the difference of things, of phase, of fluxes, where this is just delta phi AB divided by 2. So we have just joined both variables in a different one because it's more convenient for adding the cosines. And the message then is that you again have a single flux difference, accounting for these two differences. And you indeed have a potential that is the same that we had before, but now it's modulated by the external flux. Okay, I didn't lose you, did you? So it's what I promised, more or less. Okay. So what is this used for? Originally, the purpose is not doing quantum computing, of course. The idea of this device is that you have here some potential that depends on the external flux that is threading through the loop, and you can use this to monitor this flux, to measure it. So you have, basically it would be this cosine potential of phi 2 pi phi 0 with some EJ that depends on this external flux. And if we now add current passing through this loop, you get a contribution that looks like this. You can't believe me, but it's more or less intuitive. What this does is to bias the flux so that it accommodates a certain current. And this tilts the Washburn potential, making a Washburn potential, until there is a point at which you really have no trapping at all. Okay, so your system here is confined to a minimum of the flux. It could be phi plus or phi minus 0. That would be the point where you have your 0-point fluctuations. As you tilt, you are in a metastable configuration, but more or less you can remain trapped. But there is a value of the current that allows now this quantum particle to fly away and delocalize completely. Okay, so it gets accelerated in this direction. The flux grows linearly in time. That means when you have a time-dependent flux, you have a voltage, and your state changes. And you will see that the first experiments that we will show with flux qubits, they use this device for measurement, because this current depends on the external flux. So your switching happens depending on the flux which is inside this loop. So you can use this to measure the tiny currents that form part of flux qubits, for instance. But that's not what we have been using it for. We have been using it for as a tunable. So the first application would be just metrology or measurement, very sensitive with a fraction of phi 0 sensitivity. The second application that we have really used this for is as a tunable junction, EJ of phi x. So you have any design that involves a junction, you can replace this junction with a SQUID, and now that element becomes tunable, and that's the case of the charged qubits, but that's also the case of flux qubits, that's also the case of other nonlinear elements in your system. And that's the application we have been using so far. Then there is a last application, which is to use it as a tunable inductor. Now the idea is that, you have a tunable junction, but you're going to work with it in the linear regime. So you're not going to use the nonlinearity of the junction. You're not going to build a charged qubit. You can build, for instance, something like an LC resonator. Where you would like to have an inductance that can be tuned. And the idea is very simple, and it has been exemplified in many experiments. A paradigmatic one from the point of view of basic science is this Casimir, dynamical Casimir effect. The idea is that they built a microwave resonator, but in between the resonator they place one of these SQUIDs. Okay? So from the point of view of our fundamental mode of this cavity, this is like having a fixed inductance, and you add some SQUID here. This will be your tunable Josephson junction. But because we are working in a low power regime, there are not going to be nonlinear effects, and this junction can be strong. What we are doing is that we work only with the linear part and the quadratic part of the cosine. So we have this potential, that will be the energy that your system experiences, and we keep only terms up to second order, and you can assimilate this to having phi square, to having an inductor that can be tuned. More or less see it, no? So that's the cosine. We assume that the cosine is very deep, so we are never going to explore the parts where it bends. We are going to stay more or less around here. So we keep only the quadratic terms, and those quadratic terms, they are just like the terms that you would get from an ordinary inductor. The nice thing is that because our Josephson energy can be tuned, you can make this inductor tunable. And this introduces the possibility of having a resonator frequency that depends on this external flux. And that's also the basic of parametric amplification driving oscillators. Okay? There are other applications like switchable couplings. You can use these SQUIDs as coupling elements, but we will see them later on in the lecture, so I don't want to complicate matters too much at this stage. Okay, so let's move on. Now, assume you know everything we need about SQUIDs. When they show up, it will be no surprise to you. And we are going now to move away from the charged qubit, trying to improve it. So we already saw the experiments with a charged qubit in a cavity, which were really good. I mean, the lifetime of the qubit improved with respect to early iterations of groups in Saclay and Japan and so on. But still, the qubit, the coherence times or the phasing times, they were too large. So roughly, the qubit interacts very strongly with the environment, and it dephases due to charge fluctuations too quickly. We now have to discuss a little bit this kind of noise. So the idea, I'm basing my discussion on a paper that introduced theoretically the design of the transmon. Let me find the reference if I have it. Should be around here, yeah. This is Jens Koch. IPRA. Oops, I'm missing the year. 2007. I'm missing the page. Okay, well, it's probably easy to find. And I will fix the reference in the notes when I upload them. So we have this charged qubit, which has its own qubit hyperbola, like this, square root of delta square plus bias field square divided by 2 with some effective Pauli operator describing the two levels. And typically, experiments operate best around this symmetry point because it's the point where the energies of the system are least sensitive to external fluctuations. So basically, epsilon is an external voltage. This voltage can be caused by your electrodes, or it can be caused by surrounding charges that could be trapped in your dielectric or anything. So you expect that there is going to be noise in all these terms, and this noise here shifts a lot your energies. This is very large here, but here the noise to first order is approximately 0. The reasoning is that one, basically. We saw already that when we introduced dephasing, that dephasing in the end appears because you have some Hamiltonian and you have some perturbations. This is time dependent and they are noisy, so they are just random perturbations of your energy levels. They fluctuate, and when you account for this in the dynamics of your density matrix, basically what happens is that the coherences are the expectation values of these operators. They decay within a time scale, could be T2 time. We can make this a little bit more rigorous. In this, the discussion in this paper is more complete. In general, the idea is always the same. Your energies depend on external parameters, and you want to analyze how strong those variations are. In this case, they are second order. In this case, they are first order. So we can consider different situations. And we will later on compare different qubit designs, analyzing the effect of these perturbations in the dynamics of the density matrix. But the idea would be the following one. So we have a charged qubit, Hamiltonian, which we wrote as 1 over 2c q minus some externally induced charge, and Ej cosine of a flux 2 pi phi 0. And we are going to consider noise in the externally induced charge or in the Josephson junctions, both kind of noises. But let's first focus on this one, because it seems that the coupling of the charged qubit is largest to voltages, to charges, so this will be the dominant source of the coherence in this case. You can expand this Hamiltonian, and you have in the phase number representation, we had these expressions plus minus I. This would be the number operator and some external influence, Ej cosine of the phase. It will be the same Hamiltonian, but now instead of working with charge and flux, we have moved to the phase number representation that we introduced some time ago. Okay? You more or less recall this, no? We had the Fourier transform of number states, where these are well-defined number of Cooper pairs in your island, excess or defect, positive or negative. And using this basis, we introduce operators that describe the phase difference across a junction and also the charge on the system, which is this derivative. Now, if I look at this Hamiltonian, basically it looks like, oops. It looks like this. You have a cosinus potential with Ej in front of it, and you have a momentum operator, which would be minus delta phi, which is the number of particles, of carriers in that system. So basically we are studying the dynamics of the qubit around this minima, assuming of course that this guy is the dominant energy scale. However, for a charged qubit, this is not really the case, because you have that Ej over Ec goes from 0.1 to 1. So that's not really the picture that we have in this charged qubit. The dominant energy scale is this potential, and then this act as quantum fluctuations over the eigenstates of this Hamiltonian. Okay? And that is why the influence of this guy is so strong, because the basis in which we work is this one. If you now move to this other basis, what would be the effect of this term? This is just like having a term minus Bg times some momentum in your Hamiltonian. So what does this physically do? What does this describe, more or less? Can you see it? Is that you are moving with some velocity. So your wave function, so you can work with this Hamiltonian and solve this equation, or you could make a change of variables. Well, I don't know if it's exactly with the same order of magnitude. Define a new wave function, and you would get rid of this guy. Okay? Because the time-dependent time derivative of this guy pops one spatial derivative with respect to the phase. So this is the Hamiltonian of a particle in this cosine potential, which is moving at a certain speed. Okay? So when is this term going to be relevant? If the particle is confined to a single well, that particle really doesn't need to know whether it's moving or not, basically. It's just experiencing the dynamics in a frame of reference which has uniform velocity. Nothing happens. The only time where the particle will see a difference is when it is not confined to one well, when it can move to different wells. Will follow the reasoning more or less? That's a qualitative reasoning. I mean, you can make it more rigorous. But the idea would be that this term, it can be gauged away, and it's only relevant, it only changes the energy when your eigenstates are not localized like this, but they will be connecting different wells in your system. You can believe me more or less, but if you think about it, it kind of makes sense. So this suggests that a way to get rid of the effect of these external fields, at least for what relates to the charge part, would be to make these wells deep enough, to make these barriers deep enough, so that the overlap between different wave functions is cancelled. The overlap between these wave functions is basically accounted for by the solution of the harmonic oscillator around this minima. So if we can make these harmonic oscillators tight enough, the overlap between different sites will be negligible, and the eigenstates of my system will be localized at the minima of this potential. Okay? So this suggests that the possible way of getting rid of this guy, or its influence, would be to work in a regime in which Ej is larger or comparable at least to the charging energy. Any questions so far? So I'm going to put some pictures of how this looks like. The idea would be that before all this, we had a small island with two junctions that couple it to some ground plane. But now we are going to move into a regime in which the dominant energy scale is not the capacitance here, but this one. So we want to make EC smaller. We want to make the capacitance larger. Okay, so we are going to make this guy bigger. So if you look at those pictures, don't remember where I took them from. They are in the lecture notes, but you can find similar pictures in the experiments from the AI group. We're working with big structures. Have here your junctions of capacitors. This will be symmetrically placed. We make the capacitors bigger, so there is more surface for charge to be accumulated, and it's proportionally much bigger than the region where we have the tunneling between the different segments of this island. It's now an isolated structure. It's not touching anything. It's just one body describing the tunneling between two segments of capacitor with a junction that is now a SQUID as before, which can be tuned. The dimensions are much bigger than the charge qubit islands that we had before, and this is what we account for in the capacitance. And well, before arguing about the solutions of this problem, more or less the idea is the following one that you see there. So that would be the eigenstates of this problem. We have to solve an equation that looks like 4IC EC minus ID delta phi squared minus AJ cosine phi minus the energy of the given state on this wave function should be 0. This is the eigenvalue equation, which can be solved. It has a name, it's a material equation. There are formulas for the solutions for the eigenmodes and eigenenergies of this equation, and you can find them in this PRA or also in Mathematica. But there is a nicer way to look at this. It's just you take the cosine, and because we are working in a limit of large EJ, we replace this cosine with a quadratic term of this guy. And we use this to approximate the eigenstates of this potential. At least this approximation is not too bad for the first one. There would be corrections that come from terms of this form that can be also included in perturbation theory. But if you use this model, you will see that this looks like a harmonic oscillator. With a frequency that goes like 8 times EJ. See? If I did H divided by H bar, which comes simply by taking a Gaussian wave function and injecting it here, or if you want, you can say that 4EC will be like H bar to M, and 1,2 EJ will be like 1/2 m omega squared, in analogy with a classical particle, and you can get the frequency there. And that would be more or less an approximation for this first transition. The wave function here is like a Gaussian with a certain width, and this Gaussian has an exponentially decreasing overlap with the solution from a different well. So this tells you that the tunneling amplitude from here to here is going to decrease, and it actually decreases with this ratio. Okay, so you simply take a Gaussian place at this point, a Gaussian place at pi, compute the integral between both, and you get this kind of numbers. In the paper by Koch and co-workers, you will find other similar derivations based on the asymptotics of the exact solutions of that equation. That's an equivalent way of doing it. But what is important is the features that you see in the plots. On the left, you find the eigenenergies of a charged qubit. When EC is comparable or smaller than DJ, the ratio here would be 1. And you see that Ng, which is the externally induced number of Cooper pairs, which is proportional to the external voltage, induces changes in the energies of the eigenstates. Okay? Basically, here you see the parabolas that we had for the charge, of the state with charge 1 and the state with charge 0. And those parabolas, they intersect, and this will be state 1, this will be 0, and you have this. And of course, this depends crucially on Hj or Qj or the voltage that we apply. So the energy really changes with this external field. But as you increase Ej, the tunneling amplitude to neighboring walls decreases exponentially, and at some point where the ratio between them is about 50, it is really impossible to see any variation in the energy due to this externally induced potential. Okay, so basically the energies are flat. Okay. this simply tells you that we are working in a different regime. The charge number is no longer so well defined, but it doesn't mean that the system doesn't couple to anything. It just couples differently to the external fields. Let's make a break here. Okay? Okay, so we stopped at the energy level dependency on external fields, and now we are going to put some numbers about how this actually influences this design of the transmon. Just to aid you a little bit if you want to follow this paper, I'm going to just summarize the discussion. It's the one I mentioned before. You have your energy levels with whatever splitting between the two lowest energies you have. And now you assume that the energy can change with an external parameter, and this parameter is going to fluctuate in time. It's going to be induced by some environment, classical or quantum. And we want to analyze the effect of these perturbations in the state of the system. Because they are diagonal, the only effect they have is that they spoil the coherences of the density matrix. So if you analyze the expectation values of the sigmas plus or minus operators, they go like you have your typical frequency here, but you also have the expectation value of the cumulative effect of these fluctuations. Over your environment. So this would be expectation value over your environment or your noise source. You have to make some assumptions about that environment at some point. You could do the same thing if instead of being a first order contribution, it is a second order contribution to the Hamiltonian. You can have higher order terms, like when you're working in the sweet spot. Of course, this will be just row 0, 1, and 0. And just, the common assumption is to take this noise as Gaussian, which means that it can be described only with a few moments, with few expectation values of these operators, perturbations. So you would have expectation value of lambda, and so on. And if we assume that the average is 0, you only have the autocorrelation of the noise with itself. So you would have power spectrum associated to this operator, which would be this guy, expectation value of tau. And the solution to this reads t to the minus a delta x minus 1/2 the integral over all possible frequencies that contribute to this, or this power omega half square, something like this. You can more or less do the same derivation if you use your master equation from before, and this guy would be equivalent to the spectral function that we wrote at that point. Okay. The trick is that basically this is dominated by contributions around omega 0. The sink is peaked around omega 0 and is the dominant part of it. So one possible idea would be to just assume that this is smoothly varying over the interval in which this changes, and take this guy evaluated at 0 or very small frequency out of the integral. Okay. And now in this integral, you can make it qualitatively just by defining variable nu, which is omega t, so that d omega is equal to d nu divided by t. If you do that, you will see that this scales exponential of some prefactor t and then a number t2, where t2 depends on the power spectrum at very slow frequencies. So that would be an exponential decay. That's what you would get with the master equation, Markovianity, and so on. The problem in solid state and in other systems is that the value of S lambda at small frequencies can diverge. You can have very slow fluctuations in your material that are decohering your qubits or your cavities or whatever. So this analysis may be spoiled if, for instance, you have S lambda omega, like some factor with a diverging frequency dependency in your system. Okay. What happens in that case is that you have to estimate this integral, and you have to introduce some infrared and ultraviolet cutoffs to get some qualitative insight into that. And for instance, if you have mu of order 1, this would change behavior divided by 2 square, where this T2 is proportional to the prefactors I mentioned before here. But it also contains logarithmic dependence on time, a correction to these dynamics. So the behavior changes qualitatively. What happens basically is that you know that, exponential behavior in quantum mechanics at short times is not realistic. Typically you have a smoother behavior. Normally it's typically Gaussian. And because your noise acts on a time scale which is long, it has very long memory time, you never reach this, you stay in a smoother curve before that. But nevertheless, you can define some timescales for the effect of this, even if it includes some a bit hand-waving parameters like an infrared cutoff or some estimate of a power spectrum for different types of noise. So this kind of 1 over f noise, which is called like that because it's a divergent in the frequency and because it's slow, has been analyzed in the literature a lot. And if you look at the work by Koch and co-workers, what they do is basically they take the transmon model and the charge qubit model, and they introduce estimates for the power spectrum of different noise sources. And you get some estimates of how they should scale in theory. The qualitative difference is that for the transmon, we have corrections at first order, which will be, for instance, the correction due to the charge, which in the case of the charge, for instance, they are exponentially suppressed. Would be the discussion in this case for lambda. Or charges. And that means that these guys, they can be very small. For instance, if you take EJ over EC 20, 50, 100, then this derivative can be 0.07, 0.00015, and 10 to the minus 7 EC. So it can be very small, and we already saw it more or less in the plots of the energies as a function of the external voltage. And in the charge qubit, you would expect that because we work at the symmetry point, the noise appears only at the second order, which would be good, no? This is first order, this is second order, that should be worse. But the problem is that the qubit hyperbola has a huge curvature. And remember that EC is much larger than EJ, or comparable to EJ in the charge qubit. So when you put numbers there, and you use EJ over EC 0.1 or 1, you get that these quantities can be 6,400 times the charging energy, or 64 times the charging energy. Okay? So that's what it's telling you is that indeed you are at the symmetry point, but you move away, and this quickly becomes linear. Okay? So the curvature is very large, and that influences the actual computation of the noise, of the effect of noise, even if you just work with these two types of estimates and replace the appropriate power spectra for different noise contributions. I don't know if I have the table here. No, there. Okay, numbers. Well, you find them on the paper. These are theory estimates, but it's useful to see what different type of noise you have to consider. Remember that your Hamiltonian looks like 4EC minus EC over phi external cosine of the phase. So there are basically three sources of noise. One would be that you add to this some voltage uncoupled to this. So that would be one. The other one would be that you have noise in the flux you applied on the squid. And the other one would be that these, the Josephson junctions, they change. That the Josephson energies of your junctions fluctuate in some way. And they put numbers, so the nature of the first one is the one we saw before, so you have charge noise. We are talking about 1 over F noise all the time, which has a very small amplitude. So these are very small charges. And for the transmon, give a T2 estimate of 400 microseconds. It's optimistic, but that's what theory tells you. And under the same conditions, for the Cooper pair box, this is assuming EJ over EC 85, EJ over EC of order 1. This will be 1 microsecond. So this is the dominant source of energy in this guy. You have flux noise, which is simply that you are not controlling the noise that goes through your squid. That's really small. And in this case, it's just 3.6 milliseconds, and this is 1 millisecond. So that's really not an issue. But there is another source of noise, which would be critical current fluctuations. Your Josephson energy fluctuates somehow. This is now the parameters that appear in the slow noise, 10 to the minus 7 to 10 to the minus 6, the quantum of current, and you have 35 microseconds here and 17 microseconds. So this is telling you that the tunneling amplitude through the junctions can fluctuate in time. This is something that is seen experimentally. And it's attributed to the presence of charges trapped somewhere around the junction or inside the junction, and that can influence the tunneling amplitude of the Cooper pair through the device. But you see that overall the numbers seem to be better, and well, that's the message. If you go to the experiments, indeed the lifetimes are better. I will not show you numbers for planar transmons here. We are now going to move on even to a slightly different context. What's the price that you pay for having these better coherence times? Some of you works with transmons. So what would be the price that you pay for that compared to the charged qubit?
Loss of atomicity?
Yes. So you see it in that curve. When you increase EJ over EC at around a ratio of 30, you have that the energy levels, you have your ground state, you have your first excited state, and your second excited state. This would be, the splitting would be omega 1, 2, omega 0, 1. So we want omega 1, 2 to be very different from omega 0, 1, because if we are going to drive our system, we want to drive it at a frequency that would excite this transition, or qubit transition, but doesn't populate high energy levels. And for the charged qubit, we have that E of n goes like the charging energy n squared. So this is a huge harmonicity. The splitting can be 4 times the charging energy between the state with charge 1 and state with charge 2. But for the transmon, this is not the case. The energy is dominated by the cosine potential, and you can have that actually the states are compressed. So omega 1, 2 can be 90% omega 0, 1, and this compression happens as you move up and up, further up in the cosine. So the states are getting closer and closer. Like when you have a hydrogen atom, the states approach each other as you move away close to the asymptotically free states. This means that there is a time scale in your experiments. So if you are going to drive your system with a pulse of frequencies omega 1, 0, 1, and you want this pulse to only excite a 0 to 1 transition, the duration of this pulse cannot be too short, because if it's short in frequency space, the width would be of the order 1 over t. So that means you cannot drive the system faster t has to be longer than the anharmonicity, which is in this case 0.1 omega 0, 1. So there is a limit in the speed at which you can have to operate your qubits. It also sets a limit, for instance, in the strength with which your qubit can couple to a cavity. So if you want just two levels to participate, this would be just 1, 0, that's 0, 1. This coupling strength has to be smaller again than the unharmonicity, because if it becomes bigger, then a couple of photons of this guy can excite the transition to level 2 and so on. So that would be bad, because you would lose the qubit, you would end up with just a harmonic oscillator. So there is a limit on the speed of control, and there is a limit on the interaction strength that you can achieve, which is not bad, because in the end, most of these experiments are done in a dispersive regime where the coupling has to be smaller than the detuning of the qubit from the cavity already, so this is not a too strongly interacting setup. But the transmons have also a very nice feature, which is that if you look at the design that I show you in the photo, you have basically a capacitor and a SQUID principle. Why do we use the SQUID? I mean, basically we have a qubit Hamiltonian, which is going to be this splitting between the 0 and 1 states, plus some potential external field which couple to a charge and induce transitions. What happens is that with this, by tuning the junction, we can tune in principle the gap of the transmon. But you may not need it. I mean, why would you need to tune the gap of the qubit? If you design a qubit which has the right gap, I mean, delta is okay, then you wouldn't need to move it up and down. And we have seen that we can work with the qubits in a dispersive Hamiltonian. We will see also some experiments. Most of the experiments are done like that. So in principle, you might not need to tune the qubit. If you can do that, basically you can get rid of this. You get rid of one more source of noise, and you have an object which is stands by itself. So you don't need to modify or control it in any way. It's like, it's something that you could cut out of your experiment and move it from one experiment to another. Okay? So it's like a compact object that implements a two-level structure that couples to external fields. And that's the idea behind making these guys more macroscopic. This is called the 3D transmon. I'm not going to deal into many details, but the idea is that first of all, you can make this larger. So you can increase the capacitance, because the frequency depends very weakly on that. So it depends like the square root of the capacitive energy and inductive energy. So in principle, you can increase the capacitance and compensate with the junction, and more or less staying within the same gap, energy gap. I find that it's also very beautiful from the theory point of view is that the observables depend weakly on these changes. If you remember, we have the charge operator in this in the oscillator, okay, goes like the square root of 1 over z. It means that it goes like the capacitance to the 1/4. Okay, so you can change the capacitance of your transmon, but it's not going to lose coupling power because of that. Okay? Because the amount of charge that it's going to store, assuming that this works like an oscillator, is going to be very similar. But at the same time, you can increase the size. So you can make a larger dipole. So I don't know if you build these things, people can tell me the sizes of these guys, but the idea is that you can make them kind of visible, microscopic, something that you can operate with. And you can inject it, then you can now use them to couple to other macroscopic objects, like it would be the case of 3D cavities. So I put here 2 pictures, I don't know if you see them clearly. The one on the left is from an experiment of IBM. The one on the right is an experiment of Yale. I think I saw this one in the March meeting when they announced it. There was a huge commotion there about an experiment that makes a cavity that is not a chip, not a 2D structure, but a bulky 3D metallic box with a big hole in the middle where the electromagnetic field is confined. Okay? And now they take this Transmat Design and print it on a sapphire or other substrate and make the capacitors really, really big with a junction. This guy is now big that you can really hit with a finger and put inside the cavity and close the cavity. What you gain by this is that even you have movement to a cavity which is large, of centimeter size, because you increase the size of the dipole, you can couple it as strongly as you would do in a chip. And at the same time, the 3D cavity gets rid of radiation to the environment from above that you would have on a 2D chip. That's a source of the coherence in your system. This idea was pioneered by the group of Yale, and you see a similar setup on the right. You have a 3D cavity. You see half of the cavity, metallic cavity, open there, and in the middle it goes some tiny object with the transmon printed on it. Something that you can really bring in and out. And that was very nice to see that with this simple idea you can enhance the lifetime quite a lot. This is from the IBM experiment where they got 100 microsecond lifetime of the transmon by putting it in a 3D cavity. And well, these 2 ingredients. The transmon by itself is a very good qubit, which is very reproducible because the frequencies depend very weakly on the fabrication items, like capacitance that can be engineered geometrically, or the Josephson energy. So it's very robust in terms of reproducibility. It couples sufficiently strong to the environment. It has low decoherence, and now if you put it in an environment that really isolates it better, then you would have a long lifetime. But okay, so we have 15 minutes. That doesn't mean that this is the end of 2D chips, because it's still easier to fabricate 2D structures with lots of control lines and structure to it through some topology or arrangements of qubits and cavities that can be useful for things like quantum simulation or quantum computing. So people continue working on 2D setups, and that's not the end of the story. I mean, the lifetimes in 2D setups are improving as well. Let me see if I find a picture. So the Transmat Design is being evolved by different groups. The basic idea is very well established. You see in these pictures, I mean, this doesn't have to be the only shape. You can have many different shapes to change the way you couple to different lines or to various lines at the same time. And in the group of John Martinez in Santa Barbara, now Google, they had this idea of making qubits that are designed not to talk just to cavities, but to talk to each other. Okay? So this is called the X-mon. It's nothing but heavily engineered transmon with a funny shape. You have that your capacitor now has a cross structure. That's the capacitor. It's sitting inside some ground plane. Okay. So that's your big capacitance. And at the bottom of it, there is SQUID that provides you with the tunneling amplitude for this qubit. So the circuit that I draw is a bit complicated apparently. So you have something like this. And then basically all this cross is described by one capacitance, and you have a SQUID with some external flux to control it. I mean, if you want, you can just draw this, and it will be the same, okay, because these 2 points are the same, and then simply this guy couples to more things. The nice thing is that because, I mean, this is just the theory, this is the practice, so you make it in a cross structure because it can interact with at least 3 different neighbors. Okay? That's nice. But the Hamiltonian for this guy is just the Hamiltonian of a transmon, so nothing changes. One good thing is that if you improve fabrication, as they showed, you can get lifetimes of t of order 40 microseconds. So it's something that can be optimized. But it's also designed in a way that you have different coupling ports. One thing that you can do, for instance, is you can put transmons close to each other, and they can interact capacitively. Even while they are interacting, you still have other legs to operate it. Like you have still the possibility of driving some flux independently of each of these guys to tune, basically tune EJ, or basically tuning omega 01. You can shift the qubit a little bit up and down in the spectrum by changing the just some energy of the SQUID. The other thing that you can do is, because you have legs, now you can apply this idea that I mentioned some time ago, is that you can take this transmon and couple to a cavity, which can be used to control and measure this individual qubit, and you would have different resonators to talk to each of them. Okay? So it's this image of that you have more or less isolated qubits, well protected by some ground planes, only talking to each other with some interaction, and then at the same time you have a cavity that acts as a filter for some control lines that can be used to measure or operate on the qubit to drive it, for instance. So let's see it, no? And there are two controls here. This guy will be acting on sigma x, and this guy will be acting on sigma z. So you can do single qubit operations by full control of the single qubit Hamiltonian, and you have qubit-qubit interactions, which is what you need, for instance, for doing quantum information. If you want to do quantum information with qubits, quantum computing, you want to have some universal gates that act on pairs of qubits. And this layout and this design provides it. If we don't do this kind of direct qubit-qubit interaction, we would have to go for something that is based on some cavity-mediated interaction, which is the problem I posed you the other day, where the qubits talk to the cavity, and this cavity allows exchange of information between them. A little bit like what happens with trapped ions, where you have different ions talking to the phonon bath of a chain, and it's the phonon bath that provides interaction between different ions. That would be one paradigm, and this is a different paradigm that allows for direct qubit-qubit coupling. This is not a new idea. There has been examples of qubit-qubit coupling throughout the literature of superconducting circuits. This simply combines good qubits with the idea of individual controls with cavities and the possibility of achieving very flexible Hamiltonians in this way. Are you following me? I mean, it's just zoology, basically. It's looking at different designs and understanding what they are doing. So building on this idea, there is the possibility also of controlling the qubit-qubit coupling. And I'm going to use this as an excuse to discuss the possibility of switching couplings. One thing we have seen so far is that you put a qubit in a cavity, and basically you get an electrostatic interaction between the qubit and the fields generated by the cavity. In this other case of two transmons coupled to each other, you get an interaction, a capacitive interaction between the charges of two capacitors of the qubit. But one thing that superconducting circuits allow you is to tune interactions, is to have two electrical circuits through a mediator. It will be one Hamiltonian, it will be another Hamiltonian, and you create an interaction that depends on some parameter, which is typically a flux. And so ordinarily what you do is you build these guys using Josephson junctions, SQUIDs, and other ideas that engineer the coupling between different devices. So I thought it was a nice example to have a look at how you can couple transmons to each other in a time-dependent or tunable fashion. So one thing that you cannot do, of course, well, it would be a bit crazy, is to expect this mediator be a tunable capacitance. Capacitance is a geometric concept, depends on the separation between materials, and it's something that is hard to tune. So the coupling has to be inductive in some way. So we have to tune basically some inductance to allow for a control interaction between electrical circuits. For the transmon, this involves modification of the design. How can I do it? Oh, well, I will not have much time, so I will just introduce the idea today and we finish it on Friday. So you would have probably a direct coupling, capacitive coupling, but we are going to change the design of the transmon to include here a junction that is depends on some external flux. So instead of having capacitive coupling here through the antennas, what we will do is that we will couple the flux of one junction, of one qubit, with the flux of the other qubit. This will be basically this approach. What we will see on Friday is that although this circuit looks very complicated, in the end what this guy is providing with is some energy that may be controlled with an external flux that depends on the flux difference between the two qubits. This is just some potential energy, goes like phi b minus phi a squared. And in the end, it's going, once we expand this on the qubit basis of these two objects, it's going to give you some effective exchange of excitations. You can write it like this, or you can simply write it like this. And we will briefly see how this appears from just circuit theory. Okay? So this is called the gmon because the G coupling can be tuned. We have here G. But that's just names. Right? It's just two transmons that are inductively coupled. We can stop here. Any questions?